Okay, so let's look at conservation of momentum. Very important concept when we start looking at momentum and impulse and leading into collisions. So an important feature of all isolated collisions is that momentum is conserved. By isolated, we mean that no external forces such as gravitational force or friction are present. So we are doing away with the things that are normally there, gravitational force and friction, but we're going to create a perfect world here where we isolate what's going on. So what we're going to do here is we're going to look at a couple of different types of events that occur in a collision. So we have before collision, during collision, and after collision. So the way the subscripts work here, we have V1, that's this velocity initial, and then V2, this velocity initial, and then force 1 and force 2, mass 1 and mass 2, and then after the collision, V1 final, V2 final. So we rely on the relationships that we've already put together and looked at thusly into this chapter. So the impulse theorem then applied to mass 1, which would be the smaller mass in this case, we're looking at the average force to 1. Okay, so we're looking at what the force is from mass 2 on 1 over the interval of time that the collision occurred. And so we have mass 1, velocity 1, final, minus mass 1, velocity 1, initial. So we've isolated the collision between 1 and 2 to just the momentum for mass 1 and velocity 1. Then if we look at the impulse theorem applied to mass 2, we look at the average force 1 on 2, again over the interval of the impact, and the same relationships, mass 2, velocity 2 final, minus mass 2, velocity 2 initial. So we're going to be seeing a lot of this where we have what happens before, what happens during, and what happens after to help us solve these types of problems. And what we create here is boundaries. So we create a boundary up to a point, and that helps us then set the data for the next phase and then for the next phase. So force 1 is the force on mass 1 due to mass 2 during the collision. And force 2 is the force on mass 2 due to mass 1 during the collision. So we try to set up our mathematical relationships so that they make sense and that they track, and we don't lose sight and get confused and get lost in the calculation. So just like we saw in the previous example, we've got average force 2 on 1, average force 1 on 2, and we see here that in essence the average force 2 on 1 equals the negative average force 1 on 2. So Newton's third law states that at all times these two forces are equal in magnitude and opposite in direction. So you can see why we discounted the outside forces. You know, otherwise you have too much minutia in there and it'd be too hard to try to figure out. It's not that it can't be done, it just adds to the confusion. So the two forces act for the exact interval of time. So the impulse, average force 1 on 2 over the duration, is equal to minus the average force 2 on 1 over the duration. And so we just pull these relationships then back in. Where did these come from? Well, you can see them right up here and right up here into the relationship. And then what we're going to do is we're going to go through and correct the negative and positive signs, and then see if we can pull our terms together so that we have everything on one side of the equation is for the initial part, everything on the other equation is the final part. So you can see in the last step here, mass 1, velocity 1, initial, plus mass 2, velocity 2, initial. and then the same thing on the other side for the final. Okay, and so we define this then as the mathematical proof of conservation of momentum. The principle of conservation of momentum then states that when no external forces act on a system, okay, no friction, no air resistance, no gravity, consisting of two objects that collide with each other, the total momentum of the system before the collision is equal to the total momentum of the system after the collision. Okay, so again, we pull back in some of our relationships. The impulse 1 plus the impulse, or the momentum 1 plus the momentum 2 initial is equal to the momentum 1 plus the momentum 2 final. And then we can expand those. And you'll see in every case we've got initial, initial, final, final. Before, after, no external forces. So let's take a look at a pitching machine here. So we've got a problem where we're going to look at what happens to when we have a recoil of a pitching machine here. You know, the old equal and opposite reaction. So a baseball player attempts to use a pitching machine to help him improve his batting average. He places the 50-kilogram machine on a frozen pond. You can see what's coming. Going to put it on the pond. It's going to shoot a baseball out, and the thing's going to go flying in the opposite direction. Okay? So we're just looking at using that recoil and trying to determine how far back this machine is going to go slinging in the opposite direction. The machine fires a .15, okay, that's a 1,500th kilogram baseball horizontally with a speed of 36 meters per second. What is the recoil of the machine? So we're going to use impulse and the fact that we can calculate before and after to try to determine and isolate the recoil of the machine. So we've got the mass of the machine. We're going to call that mass 2, and it's identified as 50 kilograms. And then we're going to say the mass of a baseball, mass 1, is 0.15 kilograms. And the velocity that it fires that baseball out is 36 meters per second. So let's see if we can solve for the recoil of the machine based on those mass values and that one velocity. So the total momentum of the system before firing is 0. Okay? Remember, I told you, look at these problems and try to determine where the zeros are, where you can positively say, you know, we started at rest, we have no velocity, maybe there's no mass, whatever the zero is, try to determine that. Well, in this case, we've got zeros because of no velocity. So therefore, the total momentum after the firing must be 0. So we use our basic relationship. We've got all of the mass initial, velocity initials on this side. We've got everything final on the right side. So since everything then on the final side goes to 0, okay, we said so, we can set that term equal to 0. So now I can use that to move terms around inside the parentheses here, since these are both final terms, to solve one for the other. Okay, so now I have mass 1, velocity 1 is equal to minus mass 2, velocity 2. Okay, one's going to be negative because you got this thing flying in the opposite direction. So velocity 2 then is equal to mass 1 over mass 2. I just moved that mass over to the other side of the relationship, multiply it times velocity 1. All I needed was those three terms that were given in the problem. 50 kilograms, 0.15 kilograms, 36 meters per second. Boom. I've got a velocity 2 of the machine recoiling backwards. You see the negative sign? Recoiling backwards at 0.11 or 11 hundredths of a meter per second. Okay, so when we come back, we'll go ahead and continue expanding on collisions.